Here's another summary slide. So we had some terms we already knew, and then we introduced some new ones last time. So we have exothermic, which is by definition, the change in enthalpy is less than 0. Okay? That is its definition. Okay? Endothermic, change in enthalpy is greater than 0. And for the stuff that we're interested in, another way we could think about this is that an exothermic reaction, more bonds are being formed. Okay? Remember, the formation of a bond is favorable. Forming a bond releases energy. This is negative. It's contrary to how many of us kind of came into the class thinking it went. More than are broken. Okay? Breaking bonds, it takes energy. Okay? It's a positive input of energy. Whereas alternatively, for an endothermic reaction, what this means is more bonds are being broken than are being formed. And then exergonic and endergonic were sort of complementary terms, but talking about the sign of delta G. Okay? Delta G is less than 0. Okay? We have a release of free energy. It's exergonic. If we have a delta G greater than 0, it is non-spontaneous, unfavorable. We need to drive that reaction with some source of free energy. Okay? And then this illustration here was talking about sort of the direction of entropic favorability, sort of towards more mixing or randomness. This would be the direction of positive delta S. This would be the direction of a negative delta S. Okay, and so some examples we looked at last time, we said sometimes things are always positive. Okay, we can look at the signs of delta H and delta S and make a decision on whether something would always be spontaneous, always be non-spontaneous, or whether temp matters. Okay? And we looked at both an instant cold pack and the melting or freezing of water. So I received a question that I'll address really quickly here, okay? Because it's a good point of confusion. So this reaction here, the instant cold pack reaction, is endothermic, yet the freezing of water is exothermic. And the question I got was, how are these two things, compatible, given that in both cases things are getting colder? Okay, and the issue here is, don't use the word getting colder. Okay, that's sort of regular life terminology. The way to classify endothermic is that sign of delta H. Okay, don't think about what's going on with temp, because when this reaction starts, we're at room temp. Okay, and same thing with ice freezing. We have the freezing point, but that whole process of freezing happens at a constant temperature, 0 C. Okay. So again, whether something is exo or endothermic is dependent on that sign of delta H. And here, I am clearly breaking more bonds than I'm making, right? I'm splitting this apart, so I broke bonds. Whereas alternatively here, I'm making bonds, okay? And I'll show that on the next slide. Unless anybody already knows what kind of bonds I'm making when I freeze water that aren't there in liquid water, or aren't consistently there. Hydrogen bonds, exactly, okay? So again, here's another picture of my instant cold pack. It's one use once I break the water and let it mix in with the ammonium nitrate and dissolve this into my ions. This reaction is going to proceed spontaneously. I do have to put in that initial sort of energy to sort of shake it up, get it going. Entropically, it's obviously favorable, okay? I'm mixing these two things together. From an enthalpy standpoint, it is not, okay? But the net reaction is still spontaneous, or delta G less than 0. And so again, this is sort of, it's drawing heat. This says ice, which is fine. Pretend it's a cold pack. This was from a really ridiculous book. It was like for nursing students. And I'm like, is this a real life picture that they needed? So it's drawing heat out of your leg. And so what that means is it feels cold, right, to you, okay? And yes, with time, this thing is cooling itself down. But I don't want you to think about it as it's getting colder, okay? That's not really maybe the right way to think about it. So for an endothermic process, heat is entering, okay? Heat is entering this system from my leg or wherever it is. A chemical reaction is absorbing energy from its surroundings. It's feeling cold to me, okay? And sort of the reverse reaction, then exothermic. There's an exit of heat from the system. So here's sort of the example with water. If I have ice and I put in energy, such as heat energy, it melts or then it could evaporate, and alternatively, energy is coming out of the system if I go the other way. And so here's how freezing water into ice, I'm making more or new hydrogen bonds such that deltaH can be exothermic. That's over here, right? I have all of these stable hydrogen bonds, okay, this regular organization of them. Whereas in the liquid state, the hydrogen bonds are constantly being broken and reformed. They're not consistently stable. There are fewer of them overall, right? So in going in this direction, I am making a whole bunch of new H bonds. deltaH is negative. Things are getting more ordered, obviously, so I would have a negative deltaS in going from water to ice. So deltaG is only negative or spontaneous if temp is sufficiently low. We know it's as long as we're below the freezing point. And here are some visuals to think about that. When I put in heat to ice, at first all I'm doing is raising the temperature of the ice, but I'm not actually changing its state. So it's kind of the same thing of putting in heat to my DSC. Okay, I'm just raising the temp of the water and the proteins. I'm just raising the kinetic energy, and then eventually I start breaking it apart and getting that peak on my DSC curve. Kind of something similar. Once I hit this point here, rather than putting in heat to raising the temp, I switch to melting. Okay? And then once I'm completely done melting, I start raising the temperature again until I hit the boiling point. And then again, I stop raising temp with my heat and start having a phase change. Everyone cool with that? Yes, so these were just, again, sort of the signs of the ice pack. Eventually the reaction stops, right? I mean, we're gonna reach this global min here and the reaction's over, but spontaneous for a while.